We want to run massive AI image models right on our home computers. The catch is, these models are enormous, demanding far more memory than a standard graphics card can offer. The solution we've come up with is called quantization. Quantization is a mathematical process that maps a large set of input values to a smaller set, effectively acting as a digital translation. It takes the heavy, complex math of a giant model and simplifies it into a lighter format. But that raises a very natural question. If you strip away thousands of microscopic mathematical details, don't you permanently damage the images you're trying to generate? Figuring out how to compress these massive files without losing their visual fidelity is the main hurdle we have to clear to make high-quality, at-home AI practical for everyone. Let's look at the starting point. When developers train a model, they use a format called FP32, or full precision. This is the massive, uncompressed source code. But for everyday generation, what we call inference, the standard is FP16, or half precision. You might think cutting the precision in half would have the quality, but when we place an image generated at FP32 next to one from FP16, the human eye cannot detect any difference whatsoever. The variance is literally just microscopic rounding math. Because the outputs are visually identical, running anything heavier than FP16 on your home machine is simply burning through valuable computer memory for zero visual benefit. Of course, our eyes are easily tricked, so how do we objectively prove that a compressed image is truly faithful to the original? A difference map subtracts the pixels of one image from another. If mathematically identical, the result is a pure black screen. Applying a 500% gamma boost acts like a digital microscope, exposing hidden mathematical rounding errors as faint visual static. If that boosted image just shows random, low-level grain, the compression is healthy. But if you start seeing clear structural outlines or major shifts in color, it means the model is actively struggling to interpret the data. The baseline Flux.1 model in FP16 takes 22 gigabytes of storage and 48 seconds to render. Compressing to FP8 requires 11 gigabytes and 35 seconds. Squeezing into GGUF shrinks the file to 7.6 gigabytes, but dense translation forces render time up to 53 seconds. When we run those highly compressed FP8 and GGUF outputs through our difference map and boost the gamma, distinct structural outlines appear. The rounding errors are pooling together, proving that the visual data loss is now significant. This is the traditional reality of running AI at home. You are forced into a strict trade-off. You either sacrifice image quality to save hard drive space, or you sacrifice render speed to maintain fidelity. That dynamic changes with NVFP4. This is a new data format built specifically to run on NVIDIA's latest generation of Blackwell GPU architecture. This chart shows what happens when we run the exact same model using NVFP4. The file size rests at an easily manageable 8.5 gigabytes, and the render time falls to 16 seconds. Older compression methods take so long because they suffer from what we call a translation tax. The computer processor has to constantly spend time unpacking and translating the heavily compressed data before it can actually use it to draw an image. NVFP4 avoids that tax entirely. Because it was designed hand-in-hand with the new architecture, it interacts natively with the Blackwell hardware. It already speaks the computer's language perfectly from the moment you hit generate. By aligning the software directly with the physical processors, this setup removes the traditional friction of AI generation. It's an entirely different approach to how the machine handles the math. While testing shows NVFP4 does slightly shift the structure of high-contrast areas like neon lighting, it also does something highly unusual. It entirely bypasses a widely known visual flaw in the original baseline model, a heavy, artificial-looking jawline, commonly known as the Flux chin. Because the hardware isn't fighting through a clunky translation layer, it renders the facial structure with much softer, more realistic proportions. The output actually looks more natural than the massive, uncompressed original. The hardware pipeline also includes an integrated video upscaler system. You can feed it a tiny fraction of a megapixel video clip, and it will natively expand that footage into full 1080p resolution in under 7 seconds. We don't have to keep forcefully destroying data just to squeeze these tools onto our home computers. When the software natively matches the hardware, the models run faster, use a fraction of the space, and produce a genuinely superior image.